So this is the cross section of orifice plate, and in the orifice plate it is providing restriction in the channel or pipe from where fluid flow is going on. So here you can watch that in the left side the flow area is wider, and at the restriction element the flow area is compressed. Now here, as you have got the result from Bernoulli's equation, if velocity is lower then pressure is greater at the wider area, and if velocity is greater the pressure will be lower at the narrower area. Okay, so here at cross section 1, here the pressure before restriction P1 is greater. So you are watching that due to that pressure the mercury is downwards, and in the right side the pressure is lower at cross section 2. So here due to lower pressure the mercury is somehow upwards than the earlier one. Now by taking a measuring instrument between the difference of this upper layer of mercury and lower layer of mercury, we can get the height difference between these two layers. Okay, and actually this structure is known as U-tube manometer, and this U-tube manometer is giving the output of pressure difference in the form of this level difference, in the form of this mercury level difference. This H is the replica of pressure difference P1 minus P2. So this we use in formula of volumetric flow rate, and we can find out the flow rate in the orifice plate. Okay, so here in the orifice plate that I have shown how we will measure P1 and P2 difference by using a manometer here, and then we can measure the volumetric flow rate by applying the pressure difference value in this formula. P1, all these are constant, G, gamma, A2, beta, all these are constant. So only we have to measure pressure difference. We can use the data that we have got from the U-tube manometer, and we can replace it in this P1 minus P2, and then we can find out volumetric flow rate in orifice meter in the pipe using orifice meter. Okay, so this is the orifice meter which is used for measuring flow rate. Now, since the fluids are of different viscosity, so if the highly viscous, then there is a need of different type of orifice plate, and for lower viscosity there is a need of different type of orifice plate. Now see here I am showing you the different shapes and different dimensions of orifice plate. This is concentric orifice plate. Here this is the orifice which will create the obstruction. This outer dimension, the outer circle is actually same as the outer diameter or outer circumference of the pipe or channel through which flow is going on, and this is the inner circumference, which structure is making an obstruction of this much area. Okay, the outer one will provide the greater area, which is actually the inner layer of the pipe or channel through the flow is going on, and this is orifice plate internal hole, of which the hole is smaller compared to the bigger circle. Okay, so this is the internal diameter, and these are the vent hole. This is vent hole, this is drain hole. These are some mechanical fitting structure. Okay, and this portion will be outside the pipe for taking out the orifice plate or for inserting it for inserting purpose. This is the structure. So concentric means the hole is at the center of the orifice plate. Okay. This is useful when the flow of liquid is thoroughly through the pipe. But we know that there are some slurries also, and slurries are since heavier, then they cannot flow through the complete pipe. They actually flow downwards in the pipe, through the downwards area in the pipe. So for the slurries, we need this eccentric type of orifice plate. There are few more different structure. This is segmental type and this is quadrant edge. So according to the application, according to the pipe structure, according to the designing demand, we can use this different type of orifice plate. Okay. Now, what we have studied through the formula, that is the ideal case. That is the ideal case. But practically, we are having some, we need some corrections. What are those corrections? Equation 3 is not an accurate expression in actual case, that is in practical case. And we need some correction factor named as discharge coefficient CD. That has to be incorporated here. Discharge coefficient. What is CD? It is the ratio of actual flow and the ideal flow, and is always less than 1. There are in fact two main reasons due to which actual flow rate is less than the ideal one obtained from the equation number 3. The first is that assumption of frictionless flow. Whenever we derive the formula, we do the derivation in the ideal circumstances, and the rest of the practical restrictions we don't use in the formula derivation. As we know, whenever there will be a liquid flow, there will be a friction working on it. Okay. If it is in the open area flow, then the atmospheric pressure will also produce friction, and natural considerations we have to take in formula derivation. So frictionless flow is not practically possible. The amount of friction depends on Reynolds number. Okay. The more important point is that the minimum flow area is not the orifice area, but in somewhat less. So in the diagram we can see that here actually the D2 is the orifice plate area, but actual flow is through this one, which is having some laser area, and it is known as vena contacta. So these are some restrictions that we have to put in our equation as correction. So this is the completion of orifice plate, and next we will watch the Venturi tube, in which these type of restrictions can be taken in account, and we can overcome the problems which we were facing in orifice plate. Okay, that is maximum pressure drop we were getting here in orifice plate. So the problems which were facing in orifice plate, that can be overcome in Venturi meter and flow nozzle, that we will watch it again.